This question is called an example of a back titration. So in a back titration, in this question, the acid is in excess. How do we know that? Because first of all, it's reacted with the sodium carbonate, and then the remainder is made up in the volumetric flask and it's titrated with sodium hydroxide. And that means because it's being titrated with hydroxide, the hydrochloric acid was in excess and the limiting reactant must have been the sodium carbonate. So if we know the total moles of acid that were there at the start, which we do because we have the concentration and we have the volume, and therefore if we use the formula C times V over 1,000, that will give us the total moles of HCl. So what was left in excess, it's been poured into a volumetric flask, and we have taken out titers, which were 25 centimetre cube portions, and it's reacted with sodium hydroxide. And since we know the concentration of the sodium hydroxide and we know the volume of sodium hydroxide needed, we can work out the moles of the hydrochloric acid in 25 centimetres cubed of the excess. Why? Because they react in a 1-to-1 ratio. So applying the same formula, the concentration of the sodium hydroxide was 0.150 moles per dm cubed. The mean titer, or the volume, of the sodium hydroxide was 26.6, and then we times that by 10 to the minus 3 because we need to get this into decimeters cubed. That then follows that the amount of HCl in 25 centimetres cubed, or the moles of HCl in 25 centimetres cubed, because we took out 25 centimetre cube portions from this standard solution here, is equal to 0.150 times 26.6 times 10 to the minus 3 as well. That was in 25 centimetres cubed, so in the original 250 we simply scale that up. So in the 250 it's going to be 10 times as much. So that's equal to 10 times 0.150 times 26.6 times 10 to the minus 3 moles of HCl. So just to recap, in the 250 volumetric flask, the excess, the HCl that was left over, was the volume of the sodium hydroxide, the concentration, and that gave us the moles of hydroxide, and then we times that by 10 because that was in the volumetric flask, and that gave us the moles of HCl that was in excess, which is here, which is 39.9 times 10 to the minus 3. I've not put it into standard form, as you'll see why. So originally the total amount of HCl before we carried out the reaction was the volume of the HCl, which was 200 centimetres cubed, times its concentration, and converting that to dm cubed, the volume, that gave us 50 times 10 to the minus 3 moles. So if we subtract the two, that will tell us the moles of HCl that was there to react with the sodium carbonate. So all we now need to do is to look at the reaction of the original acid with the sodium carbonate. So hopefully you're able to work out that it's a 1-to-2 ratio, that we needed twice as many moles of HCl to sodium carbonate. So remember, the mass of the sodium carbonate was 627 milligrams. Hopefully you can convert that into grams. So that's 0.627 grams of sodium carbonate. We know the moles of the HCl, which was 1.01 times 10 to the minus 2 moles from our calculation here, the amount that was in excess. And therefore, because this reacts in a 1-to-2 ratio, the amount, or the moles, of the sodium carbonate must be half as many. So the moles turn all through, and that means that we must have 1.01 times 10 to the minus 2 over 2. So it's half as many moles of sodium carbonate. And therefore we can work out the MR, because we've got the mass and we have got the moles, and we know that the MR is equal to the mass of the sodium carbonate divided by the number of moles of sodium carbonate. So we've now got the relative formula mass of our sodium carbonate. So once we've divided the mass of sodium carbonate converted to grams by its number of moles, the MR of the hydrated sodium carbonate comes out to 124.2 grams for every mole of the sodium carbonate. All we now need to do is to look at the original formula of the sodium carbonate, the hydrated sodium